All right, you guys, we're going to talk about two-way tables. Two-way tables. And probability. So we're not going to have mutually exclusive events anymore. We're going to have events that are not mutually exclusive where there is overlap. For example, if we're talking about gender versus having pierced ears, okay? So you could have people who are both, right? They could have pierced ears and be male, or pierced ears and be female, whatever. So the explanatory variable in this one is gender, and the response variable is pierced ears. They filled out the table for you. Sometimes, you guys, they don't do the addition part, so just know that all the yeses should add across to the total yeses, right, whether they have their ears pierced or not. And then, like, all the males should add down, the females should add down, so you have a total. So always add if they don't give you that last row or column, okay? They don't. Anyways, suppose we choose a student from class at random. Find the probability that the student has pierced ears. So first you can define your events, like we could do pierced ears and gender or something like that, and label them with capital letters, however you want to, okay? So the probability that the student has pierced ears. So I would say the probability of P happening. So just the probability that they have pierced ears by looking at this table. Raise your hand if you can tell me the probability that any given person out of these 178 students has pierced ears. Grant. Yeah. So here's my yes, pierced ears. Here's all the males, all the females. Here's the total people that have pierced ears out of the total people in the class. So it's 103 out of 178. Okay. Now let's do the probability that they are male and they have pierced ears. So you're going to learn something new right here. Probability, I guess I'm going to use an M for male. Male and pierced ears. So here's the new symbol, right? You guys seen this before? That means and. Yes, it does mean multiply when we get to things that don't tell us the answer, but you don't have to do any math on this. You just look at the table and find out how many people are both male and have pierced ears. So someone besides Grant want to tell me how many, what's the probability out of everyone in the class of people are male and have pierced ears in this survey? Bert. That is right. 19 out of 178 are the males that have pierced ears. Okay, now part C. Is male or has pierced ears. So this is a new symbol you should write down. The probability they are male or they have pierced ears. So this means union, okay? It also means or. This guy means intersect and also means and. Okay, in statistics, our or always means we're going to add the probabilities. However, when we added probabilities before, we only added things that were mutually exclusive. Is being male and having pierced ears, is that mutually exclusive? No. Okay, there is overlap. You can be both male and have pierced ears. So first we're going to add up the probability that you are a male plus the probability that you have pierced ears, and then we have to subtract the overlap. So the probability that any given person here is male. How many total males do we have? We have 90. All right, so there's 90 out of 178 who are male. We are adding that, because or means add, to the number of people with pierced ears. How many people total have pierced ears in this group that we surveyed? 103 out of 178. And then we counted people twice, right? So I did the males this way. We did the yes pierced ears this way. Who did we double count? The 19 males who have pierced ears. You subtract those. All right? And that gives you your total of whatever it is. And we can leave it out of 178. I think it's like 174. Anybody do it? 193. Yeah, I think so. All right. You never have to reduce. You can just leave your fractions like this. If you want to make it a decimal, I suppose you could, or a percentage, you could, or whatever. So this is called the general addition rule for two events. If A and B are any two events resulting from some chance process, the probability of A or B happening is always equal to the probability of A plus the probability of B minus the probability of A and B. So this is always the overlap. It's what you counted twice. And it's always both happening at the same time. Good news, this is on your formula sheet for the AP Stats exam, that yellow sheet that you guys have. Only it looks like this, which means the same thing. Okay, we have the symbol for union, which means or, and we have the symbol for intersect, which means add, or and, sorry, and. Okay, so you guys, this is when the events are not mutually exclusive. We talked about what do we do if they are mutually exclusive? Which part of the formula do we not need? Right? If I'm rolling 2 dice, I'm doing the sum of 2 dice, what's the probability of getting a 5 or a 6? What do? We add them. Is there any overlap? No. So you're just doing the probability of A plus the probability of B, because what should this equal if your events are mutually exclusive? It should equal 0. There is no overlap if they are mutually exclusive. Do you get this formula on the exam? No. You only get the one that looks like this, but you have to know the probability of them both happening at the same time is 0, so you don't have to subtract if they're mutually exclusive. Okay? But in all these two-way tables, you're going to have overlap. All right? Let's try to make the table ourselves based on what we know about cards. So a standard deck of playing cards with jokers removed contains 52 cards in 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. The jack, queen, and king are referred to as face cards. Imagine that we shuffle the deck thoroughly and deal 1 card. Let's define our events: F as getting a face card and H as getting a heart. Make a two-way table that displays the sample space. So you guys try to make a two-way table. And so you're going to have face card, not face card. And you're going to have heart, not heart. And you want to start with your totals. Okay? You can go either direction. You can put the heart, not heart on the top, or the heart, not heart on the side. Okay? And you can put the face card, not face card on the top, or the face card, not face card on the side. You can decide. Okay, so now let's answer some questions. Find the probability of being a face card and a heart. So the word and means they're both happening at the same time. So Matt H., what do you think is the probability of being both a face card and a heart? I agree with you. 3 out of 52. Or 0.058. Okay. Explain why the probability of a face card or a heart does not equal the probability of a face card plus the probability of a heart. Right? This is what we were doing last time, where all you had to do is add them together. How come we don't just add the first 2? What's missing from this formula? Kenny? The overlap. All right? So now let's use the general addition rule to actually solve this problem. So we want the probability of a face card plus the probability of a heart minus the probability of both happening at the same time. So Grace, what's the probability of being a face card? Yep, 12 out of 52. Plus, April, what's the probability of being a heart? Okay. And then we have to subtract the overlap. So Haley, how many are both face cards and hearts? Good. And then we get our lovely answer of 22 out of 52. Okay? So are these events mutually exclusive? No, because they can happen at the same time. You can be both a face card and a heart. That's why we subtract the overlap. All right? All right, students in an urban school were curious about how many children regularly eat breakfast. They concluded in a survey asking, do you eat breakfast on a regular basis? All 595 students in the school responded to the survey. And so here's our two-way table, male, female versus eats breakfast, does not eat breakfast. So if we select a student from the school at random, what's the probability we choose a female, Pete? I agree with you. 275 out of 595. What's the probability someone eats breakfast? I'll just use a B here, represent probability that they eat breakfast. Tori, what do you think? Yep. So the total that they eat breakfast, 300 out of 595. All right, how about you're both a female and you eat breakfast regularly? So when you do your little like probability thing, you would want to say F and B, both happening at the same time. So use the and symbol, okay? A female who eats breakfast regularly. Alexis, what do you think? I agree with you. 110, those are the females who eat breakfast regularly, out of 595. Okay, so of course now they're going to ask us both. So for D, you're a female or someone who eats breakfast regularly. So when you do your little set up this probability part, you want to use the symbol for or, which means we are adding probabilities. So we need to use the whole formula here. So Charles, what's the probability of being female? What'd you say? Yeah. So we start with 275 out of 595. Then we add the probability of anybody that eats breakfast. Patrick, oh, what's that going to be? Yes. They set this up so nicely for us. Minus the overlap, which Grant is what? Good. And so let's see, what is that? 575, so 465 out of 595. All right. Everybody understand the general addition rule? Great. That is it.